Okay, so we're at this idea of perspective projection. So this is our projection, which will produce an image on the projection plane, which is perspective, which has the depth information. So objects which are distant from the virtual camera will appear smaller compared to similar sized objects which are nearer the viewpoint. So as with everything, we want to do everything with matrices, okay? Because the positions of the objects are represented by the vectors, so we want to carry out the operations on them with matrices. So to carry out perspective projection, it's going to be a two-step kind of process. We're going to use a matrix multiplication by an appropriate projection matrix, but then we're also going to use the convention for treating homogeneous coordinates and converting homogeneous coordinates to kind of standard normal coordinates, which we did mention when we first introduced them, but this is the one point where we make use of it. Normally we think of the homogeneous coordinates as just being kind of dummy, kind of fourth coordinate, whose kind of role as we set it up, its role was to enable us to carry out translations using matrix multiplication. But it's also kind of useful here in allowing us to implement the projection. Okay. So first of all, so we want to take, the problem is, given the setup for this scene, so what's the setup for this scene going to be? So the viewpoint is at, we take it that the virtual environment has been aligned. So the viewpoint is at the origin. We know the coordinates, we know the four-component homogeneous coordinates of points in the environment, and we know the distance of the projection plane from the viewpoint, so that's the distance f there. And so we want to calculate what the x and y coordinates of these projection points on the projection plane are. Okay, so that's the problem that we need to solve. Okay, so we'll treat the general point R. So we'll have a vector R, which have components x, y, z, and 1. So that'll be a typical point in the environment. Okay. And the first thing we're going to do, well, yeah, it's a two-step process. So we have a projection matrix, P, which is given there. Now, P has a very special form shown there. And so let's look at the result of multiplying the vector R by this projection matrix. And we'll justify the whole process in a moment with the sketch of the situation. So that's going to produce the components. Well, you see the upper 3x3 block is just the top left 3x3 block in P is just the identity matrix. So that's going to leave the x, y, and z coordinates alone. But the presence in the fourth row of this 1 over f factor, when you multiply, and the 1 over f here and the 0 here, when you multiply that into the homogeneous coordinates, that produces a the fourth component there to be z over f. Okay, because this 1 over f here gets multiplied by the component z. And so that's the only contribution to this fourth element of the image vector. So we started off with our point in the scene, which had the fourth homogeneous coordinate equal to 1. Okay, so we require that to be the situation before we start. So then we have a point, so it's still got the same x, y, and z coordinates, so nothing fancy has gone on with them, but the fourth homogeneous coordinate has changed to z over f. Now we did mention at the start, when we introduced homogeneous coordinates originally, back in chapter 1, we mentioned that for the most part, that fourth scale coordinate will always be 1. But if it isn't, what we said, and this was the convention we introduced. If you have a set of homogeneous coordinates x, y, z, s, where s isn't 1, the point in 3 dimensions that that set of homogeneous coordinates corresponds to is the point with x, y, and z coordinates which have each been rescaled by s. So divided by that 4th scalar homogeneous coordinate. Okay. Now, if that's equal to 1, as it normally is, that doesn't make any change to the x, y, and z, to the first 3 components. When you divide them by 1, they still have the same values. But when that 4th component is not 1, that's when the x, y, z, and s will change. Okay. So the actual point in 3 dimensions that corresponds to, the x, y, z, s, will correspond to x over s, y over s, z over s. So if we apply that convention to our homogeneous coordinates here on the right of the matrix multiplication, our x, y, z, and zf, the point in 3 dimensions that corresponds to is this point here. X, f over z, y, f over z, and the 3rd component being f. Okay. So and the claim is that this is now the projected point. This is now the coordinates of the point on the projection plane. And in particular, those first 2 components, the xf over z and the yf over z, are the important coordinates, which will ultimately become the x and y coordinates of the pixel on the screen that's going to light up. Okay. So in order to justify this, we're going to draw a side view. So I guess this is exercise 7.2. We'll draw a side view. So by a side view, I mean we're seeing the vertical y-axis and the z-axis extending into the screen. So if you use your left-hand rule, the x-axis is coming up out of the page at you. Yeah. So the x-axis is my pen there. Now the projection screen is somewhere here. Remember, the center of view, the camera is always here at the origin. I'll just do a little sketch of an eye there. That's the virtual camera at the origin. The center of view, the point that the eye is facing, is pointing towards, is on the z-axis, because we're dealing with an aligned environment. And so this line here is the projection plane. Now this is specified by a distance f. So the projection plane is located at a distance f along the z-axis. So somewhere out here, let's draw approximately here, somewhere out here will be the point R. Now what aspects of R can we see exactly on the page? Because we're looking at the side view, we see exactly the z coordinate of R using the notation that we set up here in the notes. And we're also seeing in this diagram the exact y coordinate of R. We can't see the x coordinate because the x-axis is coming vertically out of the page at you, so you can't perceive the x coordinate. Now, but what point is that going to get projected to? Well, of course, make that a straight line. This is going to go to the point R prime, let's say. We need to figure out what are the coordinates of that point R prime, which is the projection of R onto the projection plane. Well, it's not too hard, okay? It's not too hard to see. Here we've got a line going through the origin, so that's just specified by its slope. So this is the projector line. you can see what its gradient is, what its slope is. It's got gradient y over z. Simply. It's gradient relative to the z-axis. And so what's the y-coordinate of this point here? Well, that's simply, you know, the horizontal coordinate of it here is f. And so the y-coordinate, because the gradient of this line is y over z, the y-coordinate is simply going to be f y over z. Fy over z, but that's exactly the y-coordinate of the point which came out of our matrix multiplication. Yeah. So R prime has second coordinate y f over z as required. Okay, so it's just a bit of simple, well, just a bit of straight line geometry there to confirm the claim in the notes. Now that's a side view of the situation, so we're not seeing anything going on in the x-coordinate because we can't see it on that diagram. But if we did a top view of the setup, you know, a similar kind of thing would be revealed to do with the x-coordinate. So a top view, in a top view, what would you see? Plan view from above, you'd be seeing the z-axis and the x-axis. The eye would be here. The projection plane will be somewhere here. So you could take a general point out here. That is f there. So this is the vector r. Here we want to see the vector r prime, the projection of it. There's the x-coordinate of the original r, and so it's just a question of what is the x-coordinate here. But just by treating, again, the projector line has gradient x over z, yeah, isn't it? X over z. And so r prime has first coordinate, first component, fx over z. Sorry, hang on. Sorry, things are swapping around. It's got gradient z over x. Yeah, and so again, if the z coordinate here, if the vertical coordinate in the diagram is f, the horizontal coordinate has to be fxz. So by gradient of the projector line, I mean the gradient in the normal conventions for drawing a diagram on the plane. Okay, so it's vertical coordinate divided by its horizontal coordinate. Okay, and so this again confirms the method in the notes. So we've got this two-step process, multiplying by this projection matrix P, which is given there, and then applying the convention for rendering a point with homogeneous coordinates. to getting the point that that represents, okay? And that convention is that you rescale the first three components by the fourth scalar homogeneous coordinate, okay? So is that okay? Any questions about that? Okay, so you can see, you can appreciate how it's, you know, not going to be too much of a task to implement that onto the computer, okay? Because the individual steps simply make multiplication by an appropriate matrix, and the matrix is specified once you specify the distance of the projection plane from the viewpoint. So that's part of the setup of the situation. And then it's simply applying this rescaling convention to interpreting homogeneous coordinates. Okay. Okay. So that's how perspective projections are produced. So in this way, you can take any point in your aligned world space. The distance f is specified. The viewpoint is at the origin because it's aligned. So then you just apply that matrix multiplication and interpreting the homogeneous coordinates. And that gives you then the x and y coordinates. Of course, I didn't emphasize it. Look, see, all these points here, these projected, the coordinates of the projected point, the projection point, they all have z coordinate f. Yeah, f, you know, the third component is always f, and that agrees with the fact that we're talking about all these points on this projection plane, which is a plane parallel to the xy axis at the distance f along the z-axis. Okay? So the z-coordinate of all these projection points, so the points in the projected image of the house thing there, they all have z-coordinate f, as they should, okay? Because they're all living on this plane parallel to the xy axis, which is located at z equals f. Okay? So the point about perspective projection is it has this, it carries the depth information. Okay, so you can perceive by looking at the image, you get an impression of how far away things are due to their relative size. Of course, that can also be a disadvantage. It can also be misinterpreted, and that's what was troubling Father Dougal Maguire with the cows. The cows in the field looked the same size as the model cows he was holding in front of himself, and that was what was causing his understandable confusion. And it's only because we're familiar with the size a cow should look. You know, plastic cows are an aberration, really. Cows are these kind of objects which are about this tall, so we know how big they should be, so that when we see the image of a cow in our minds, we can judge how far away it is, because it's well, if it's far away, it will have shrunken from what we know its size to be. Okay. So associated with this phenomenon, how things look smaller the further away they are, we have this idea of vanishing points. Okay. So here we're viewing some kind of a basic building type object. Or you can get this impression when you stand in a street with a straight street, say with buildings of much the same size. When you look down the street, you see that the building or the street itself, if it's long enough, seems to be, and the two sides of the street seem to be coming together and meeting perhaps at a point in the distance. Okay, so these are called vanishing points. And so they arise when you have parallel lines in the real world space. When they're projected onto the projection plane, these lines are no longer parallel, okay? And if they were continued long enough, they would appear to meet at a point, okay? And this point is called a vanishing point, okay? Now, different families of parallel lines. So one family of parallel lines here is the top and bottom edges of the white face of the cube there. and these front and back edges of the gray face of the cube, they're all parallel to each other in reality. And so those lines in the projection are all meeting at this vanishing point V2 over here. There's another family of parallel lines, the top and bottom edges of the black face, and this kind of left and right, well, it depends which way you're looking at, but this edge of the gray face and this other edge of the gray face here. In reality, if this is a cube or a rectangular box, in reality, those lines are all parallel to each other. But in the perspective projection, if they're continued on long enough, they appear to be getting closer and closer. And if they're sufficiently long, if they disappear into the distance, then they actually seem to meet at a certain point on the projection plane. Okay. So we can set ourselves a little problem here, which is to determine where these vanishing points are. Okay. So given the setup of, given some kind of setup, where are these vanishing points? So that's the problem we're going to tackle now. And just to be clear, in this world, in this environment, any other line which is parallel, so this edge that the mouse cursor is at now, any other line in the environment which is in reality parallel to that line will go to the vanishing point V2 as well in the projection. Okay, so if there's some other line way over here on the other side of the, away from the building, but if in the world space, if it is parallel to that edge, it will be disappearing to the vanishing point V2 as well. Okay, so all that's important is the direction vector of the line. Where in the environment the line is situated is not relevant for determining what the vanishing point is. But how does that come about? Or can we track the calculation that will tell you what the vanishing point is given the direction vector? Okay, so this is exercise 7.3. So show how to determine the location of a vanishing point in the projected space. That is, where is the vanishing point for a family of lines parallel to a given direction vector h in the world space? Okay, well, every line in the world space which is parallel to h, parallel to this direction vector h, this has an equation. The line has some kind of equation with vector equation, which is p plus mu h. Okay, where p is just some reference point on the line. P gives you the actual position of the line in the world. Okay, so for some reference point p. So we're imagining here a bunch of different lines, but they all have the same direction vector h, but different reference points p might determine different lines. Okay, so there'll be one p for the bottom edge of the white face, there'll be one p for the top edge of the white face, and so on. Okay, so different p's refer to different lines, but if you keep the same direction vector h, all these lines will be parallel in the world. Okay, suppose the projection plane, so part of the setup is the position of the projection plane. So we'll suppose the projection plane is located at z equals f. As it has been in the treatment we gave of it before. Then the projected point r prime will have coordinates Now, where will the projected point r prime will be? It will have coordinates rx, ry, sorry, call these r prime x, r prime y, f. Given by, so we're going to say here what r prime x is and r prime y. So we'll use the usual notation. We'll suppose P is the vector Px, Py, Pz, and H is the vector Hx, Hy, Hz. So we're not dealing in homogeneous coordinates here, so we're just doing the vector analysis of the setup. So it's simpler if we just deal with normal coordinates as opposed to homogeneous coordinates. The homogeneous coordinates are really only used in the implementation of it into the computer code or whatever, just so everything, including translations, can be done with matrices. So, just from the formula, from this kind of form of the projected point here, you see the first component of the projected point is, well, the first component that the vector had, or that the point had originally, multiplied by this thing f over z, where z is the z coordinate it had originally. Okay. So what that means for us here is that r prime x will be equal to f into px plus mu hx. Okay, because that's the x coordinate that r has up here. This is what rx is, divided by the z coordinate, pz plus mu hz. And similarly, r prime y, the y coordinate here of the projected point, will have a similar form, except in the numerator it will be py plus mu hy, all over, again, pz plus mu hz. Now, where is the vanishing point? Where is the vanishing point? Remember, so for what's going on here, the actual vector r will be determined by whatever value this parameter mu has. As mu changes, the point r moves backwards and forwards along this line. Now, the vanishing point is the point when you go really far out along the line, okay? They don't exist in reality. It's just the impression that we get that the lines are getting closer and closer together. So really, the position of the vanishing point is obtained when you take the limit as mu goes to infinity, okay? So imagine the direction vector is kind of pointing away from you. Then when you let mu go to infinity, that's going to give you the position of the vanishing point, okay? Where the points on the line are approaching as you go further and further out along the line, okay? So we want the limit as mu goes to infinity of r prime x and r prime y, okay? Because those will give us the x and y coordinates then of the vanishing point for this line, and all other lines parallel to it, hopefully, in the environment, okay? So let's just try and take one of these limits. So we're going to take the limit as mu goes to infinity of r prime x, which is the limit as mu goes to infinity of this quantity f, px, plus mu h of x over pz plus mu h of z. So I'm going to take the limit of all that as mu goes to infinity. Now, everything in there is, don't get discouraged by the fact there's lots and lots of variables there. They're all part of the setup. These are f is where the projection plane is. the px, the pz, they're components of the reference point, so that will be given to us. And the hx and hz, they're components of the direction vector of the line, so that's part of the setup. So everything is part of the setup, and you have this parameter mu that you're taking the limits of. So this should be an evaluatable kind of thing, limit. Yeah, question. Well, okay, so if you're talking in terms of pixels, yeah, okay, well, yeah, there might be difficulties there because the position of the vanishing point might be between some pixels or that. But we're not to, I think we're talking about an idealized situation here. So we're talking about the projection of the 3D environment onto the two-dimensional projection plane. So we're still in a continuous space. So we're still talking about positions of things with real components. Obviously, yeah, but when you come to the actual transferring it onto the hardware of the screen, then you have to deal with approximate positions because there's like a quantized distance, which the minimal distance you can have is the distance between pixels, which is whatever many thousandths of a millimeter or whatever it is. So yeah, you run up against difficulties of implementation there. But here we're not talking about this on the level of pixels, just on the two-dimensional plane of the screen. Yeah, but it's a good thing to think about. Now, how do we take the limit of this? Well, the problem is we've got this quantity mu going to infinity, and here's mu in the numerator and in the denominator. So that, you know, we can't just simply say it's the limit of the top divided by the limit of the bottom, because the top, as it stands there, isn't going to a limit. It's going to infinity, because it's got mu there, and so is the bottom. But, you know, if you recall from when you were dealing with limits last year, we can resolve this because mu is present in both the numerator and the denominator. We'll simply divide above and below by the quantity mu. So that will change the numerator now to px over z plus h of x and pz over, sorry, not over z, mu. Mu. So it's px over mu, pz over mu, plus h of z. Now this limit looks a lot better because the parameter mu is going to infinity. And where is mu occurring? Well, it's p of x over mu, p of z over mu. So mu is getting larger and larger. So these little fractions here are both going to tend to 0. Okay? So quantities px and pz, they're fixed. They're part of the setup. They're the components of the fixed reference point. So px and pz aren't changing. But just the mu in the denominator of those little fractions is getting larger and larger. So those fractions are going to go to 0. And so this will just be the quantity f h of x over h of z. Since p of x over mu and p of z over mu, these are both going to 0 as mu goes to infinity. So we get a fixed value for Rx prime. It's determined by f, so that's where the projection plane is. That's part of the initial setup. It's also determined by the components hx and hz, and they're part of the specification of the line in the environment. They're the components from the direction vector of the line. Okay. So this shows you how the x-coordinate of the vanishing point, the x-coordinate of the projected, the first coordinate of the projection of the points on this line, as you go further out and further out along the line, those x-coordinates are approaching this fixed limit, f times h of x over h of z. So this is the x-coordinate of the vanishing point. So this is the coordinate, the first coordinate, the x-coordinate of the vanishing point for this line. Notice that it's independent of the position vector p. It only depends on the direction vector h. Okay, it depends on f as well, but f is part of the setup for the overall thing. So it's note it only depends on h, on the vector h. It's independent of the position vector p. So no matter what position vector you choose, you always get this same limiting value for the x coordinate of points on that line. Remember, choosing different reference points p will give you different lines. But if you're using the same direction vector h, they're all parallel to one another. So that's why, points on these three different lines here, when you take mu to infinity, although they're always different points, they're always different points in the projection, but as you take the limit as mu goes to infinity, their x coordinate is all approaching the same value, whatever the x coordinate at this point v2 is. Okay. And quantified in terms of the setup, it's this quantity f hx over hz. Similarly, and you can do the calculation for the y coordinate, but you can kind of guess what it has to be. Similarly, r prime y, the limit as mu goes to infinity of r prime y is going to be f hy over hz. I mean, it has to be. But you can follow through the same kind of calculation here, and you'll see that. Okay. So this shows how to determine the vanishing point for any line parallel to this direction vector h. Sorry. Yeah. There's maybe one special case. I mean, well, there's one situation where what I've said wouldn't be valid, and that's where the the coordinate hz is 0. Okay, because then this would be nonsense. I can't put a 0 in the denominator position. But what's the setup when h of z is 0? When h of z is 0, that means you're talking about a direction h in the aligned world space which has no z coordinate. So that means it's a direction that's parallel to the xy plane. Okay. Parallel to the xy plane. So that means there won't be a vanishing point. Okay. Because those lines, under the perspective projection, those lines will always be the same distance apart, because there'll be lines that are running parallel to the xy plane. Okay. So this is valid as long as h is valid, provided h of z is non-zero. That's kind of difficult to appreciate. I mean, how can I explain this to you? So I'm standing here, I'm seeing the two edges of the rows of seats. So they seem to be moving towards each other. In reality, they're not, because in reality they're parallel. It's the same distance between the stairs have the same width here at the bottom than they do at the top. But I'm perceiving it here. It looks slightly narrower there, okay? Because those lines are going into the distance. So there's a vanishing point for those lines. If you look at the back of the lecture hall there, there's this kind of grill cut out on the back wall there. So there's vertical lines going up and down. You just turn around and there you can see all these gray slits on the back wall. So there's the vertical lines produced by the edges of those gray slits. Now, the direction vectors for those lines have no z coordinate, because they're just, I presume they're just going exactly vertically up. So they're direction vectors relative to the viewing plane, which is the plane straight in front of me here. They have no z coordinate. So as I'm looking at a particular point there, those lines are, I don't perceive those lines to be getting closer and closer or anything. They're just the same distance apart in the image that I'm seeing. Now, if I stood close to them and kind of look up along them, then I'll perceive a vanishing point effect. But you see, when I'm changing the viewing direction vector then, okay? So if I stand, they're the same lines here. If I stand underneath this grill, can't quite do it with the microphone. If I stand underneath this panel here and look up, okay, I will see a vanishing point for the vertical lines, but then I'm changing the direction of view, so I'm changing the whole alignment that has to be done. And so then the direction vector for those lines then does have a z coordinate, okay? Because I'll be looking up, so that the projection plane will be tilted, be some kind of 45-degree plane as I look up towards them. But then their direction vectors do have a z coordinate, okay? Because they're moving away from the projection plane. But if I'm just standing here and looking directly straight horizontally towards the back of the room, those lines are parallel to the projection plane. So there's no z coordinate, so there isn't a vanishing point. Okay? So, you know, it's a useful idea, and they're useful things to use as inputs into how to construct accurate perspective drawings by hand. If you were doing it, you know, as traditional artists would, trying to produce a perspective image on the plane, you can make use of these vanishing points in order to construct the drawing. We're coming at it from the opposite way. We're starting with the actual 3D data of the scene in the computer memory. So we're pushing it, we're able to produce the perspective projection directly. And we can determine the locations of these vanished coordinates, these vanishing points from the original 3D data, okay? But looked at a more kind of traditional artistic way of how do you produce perspective drawings on the page? Well, the artist doesn't have access to the actual 3D information. They're just going on what they perceive. They're just going on their impressions. So in that situation, you actually use vanishing points as a way to construct the image. Okay? And you can plot vanishing points on the horizon of your picture and extend the lines emanating out from that, and it helps you construct the image on the page. Okay. So, okay, any further thing I could say about that, do you think? Okay. Another problem, which is slightly trickier, is this notion of back projection. So this is sometimes needed in kind of interactive virtual environments, such as a computer game or something. So what's going on here? Well, it's kind of, back projection is the process where you reverse the projection procedure. Now, formally, mathematically, projection isn't invertible. If you think of like a mathematical transformation, a mathematical function, a function is invertible if and only if it's one-to-one and onto. Okay, but projection, of course, is inherently non-invertible process because there are an infinite number of points that are all projected down to the same point. Okay, when you're talking of a perspective projection, back up here, you know, this one single point at the apex of the roof here on the projected plane, every single point along the projector line coming out from that, all those points get projected onto that point, okay? So it's not a invertible operation. There isn't a unique point in the environment which is projected to this point in the projection plane. There's a whole infinite number of them, the whole line's worth of points that are projected down onto that single point. Yet in some situations, and when you think about it, when you're playing a computer game like this, your actions with the mouse or whatever they are with reference to the two-dimensional screen. If you take your mouse and you click somewhere on the scene, well, all that the mouse provides is some X and Y coordinates on the screen. So there is this problem that if I click somewhere on my view of the 3D environment, how do you try and reconstruct what point in the world space I'm clicking on? Okay. Now, there isn't a unique answer to that. If I click, imagine I'm playing this computer game here, and my mouse clicks at some point on the projection plane. Think of the projection plane as being the screen. My mouse point clicks at some point there. In order to simulate the environment, maybe I'm clicking on something to shoot at it, or clicking on something to poke an object. The point is, how does the computer interpret that mouse click? How does it decide which point in the 3D environment I'm clicking on? And it's not a well-posed problem like that, because there's an infinite number of points I could conceivably be clicking on. Because extending out, into the 3D environment, behind that point I'm clicking on is a whole line. So how does the computer know which point in the 3D environment I'm intending to click on, so to speak? Well, that's this problem of back projection. Now, as it's posed just like that, it's not a well-posed problem. It doesn't have a solution. So there's an infinite number of possible points I could be pointing at in the environment. But if you adapt it slightly, if you supply some more information, then it can be solved. So there's a simplified setup here, which we'll describe and we'll solve next time. So here's part of a scene. So there's a line between P1 and P2 in the real 3D environment. That line, under perspective projection, gets projected to a line in the projection plane, or a line on the screen, if you like. Now, if I come and click at some point on that line, and if my click is recorded as not only an X and Y coordinate, but also recorded as a click on this particular line, then as long as we still have the 3D specification of the line, as long as we still have the actual coordinates of P1 and P2 in the world space, so they're three-dimensional information, then we will be able to recover which point in the 3D environment corresponds to that point on the screen space that I clicked on. Okay? So if you think of what's going on in this picture, if I point to some particular point here, well, I might as well point to this one that the line is. So where the mouse is pointing there is some particular point on the projection plane. If we add the requirement that the point in the real environment has to lie on the line that produced this projected line, then there is a unique answer. And if you extend this line out, you see, it will intersect the line between P1 and P2 in a unique point. Okay. So back projection now is the process which takes as input the points P1 and P2 and their projected images, and some kind of click like this on a line, or some kind of point on the projected line, and is going to reconstruct for us where, what's the actual three-dimensional position of that point we've just referred to in the actual world space. Okay. So we'll have a go at that problem on Monday, treat that problem on Monday. There's some complicated algebra behind it, but we'll be able to make use of the computer to help us to do it, I think. Okay, we'll leave it for this morning.